Very good morning to all of you. We are going to start our lecture, and till now, under bulk metal forming processes, we have covered rolling and we have covered forging processes. Okay, and now we are going to start extrusion processes. This is a kind of bulk metal forming processes, and mostly extrusion processes are you can say compressive type uh, uh, bulk metal forming processes. Okay, so this was the initial diagram which was explained to all of you. I hope all of you remember that in under extrusion processes we have one one container, then we have die. Okay, and your this is your initial workpiece, which is forced to pass through a die with the help of some ram arrangement. Okay, so this metal block is extruded through this die opening, and this is your final product, which is you can say which is produced using extrusion processes. Okay, so today we are going to discuss different capabilities of extrusion process, uh, how this extrusion process is done, and what are the what kind of shapes that or products that can be generated using extrusion process. Okay, and obviously some analysis part also, that force requirement, energy requirement, we are going to cover in today's lecture. Okay, so I will try to finish that if we can finish the whole extrusion processes in today's lecture itself, so that we can complete bar and wire drawing in tomorrow. Okay, so we will go a little bit fast. Okay, so under extrusion processes, as I already told, the metal block is forced to flow through a die opening to produce a desired cross-sectional shape. Okay, so this cross-sectional shape may be a round, maybe hollow circular, maybe rectangular. Okay, so these cross-sectional shapes are generated using using extrusion processes. I think most of you have noticed your door opening. Okay, in your houses you might have seen there are L-shaped steel bar. That those steel bar are produced using extrusion processes. Those cross section, L cross section, or even girders. Okay, in the roof you might have seen girders in old buildings. Okay, so even so this kind of cross sections are you can say are produced using extrusion processes. Okay, so in order to understand how this extrusion process is carried out, you can take example of simplest example of your toothpaste. Okay, squeeze of your toothpaste. So if you squeeze your toothpaste from one side, and there is opening at the neck. Okay, there is opening at the neck, and your paste is coming out of your tube. Okay, how this paste is coming out? We are applying certain force on the one side of your toothpaste. Okay, toothpaste container. Okay, as soon as we press this container, certain force is applied on the paste, and it comes out of your neck. Okay, so you can compare your extrusion process similar to the squeezing of your toothpaste. Okay, and the advantage of extrusion process are there are number of shapes that can be generated using extrusion processes. The microstructure and strength are enhanced with the help of extrusion process, as well as if you go in terms of accuracy, the close tolerance are possible in the case of extrusion processes, especially in the case of cold extrusion. Okay, so it is obvious in all bulk metal forming processes the cold forming give more close tolerance as compared to hot processes. Okay. Also, there is one greatest advantage of extrusion process, that there is a no wastage or sometimes very little wastage. Okay, very little wastage of material in the case of extrusion operations. Okay, so there are different. Now we will come to the classification of extrusion processes. How these extrusion processes are classified. So there are various ways. First, first way is by the configuration of your arrangement. Okay, so this by the configuration, it is called direct extrusion or indirect extrusion. Okay, so this direct extrusion is sometimes is called as indirect. This direct extrusion is sometimes called as forward extrusion, and and indirect extrusion is called as backward extrusion. Okay, so this we will discuss in next slide, that what is direct extrusion and what is indirect extrusion. Okay, then this is common under bulk metal forming processes. We can classify cold, warm, and hot extrusion. Okay, so similarly, the extrusion processes are classified as cold, warm, and hot. And there is one more classification which exists in the case of extrusion processes, that is a continuous or discrete process. So by as the name indicates, continuous means there is some continuous type of production, and under discrete there is set of products that are produced using extrusion processes. One set is produced, then another set is produced, then the next set of product is produced. So this kind of extrusion is called as discrete extrusion. Okay, so now we come to the direct extrusion. So direct extrusion is mostly in most literature it is known as forward extrusion. And here you can see we have a container, a big container, under which a die is kept. Okay, so this is your die. In gray color you can see this is your die. Okay, and your metal block is placed in this container. Okay, and as soon as this metal block or work plate is placed in this container, there is some ram arrangement through which some force is applied. Okay, this if this force is enough to force this work plate to to be extruded through this die opening. Okay, so as soon as this force is applied, your material start coming out of this die opening, and this is your final work shape. Okay, that is produced using this kind of arrangement. Okay, so under this you can see the direction of force as well as of material coming out, it is same. Okay, it is from left to right. Okay, so under direct extrusion, the material is extruded in the direction of force applied. Okay, the force is being applied from left to right, so material is being extruded from left to right. Okay, so here you can see, as soon as this ram reaches till this die touches this die. Okay, so there this whole material cannot be extruded using this arrangement. Okay, why this whole material is cannot be extruded? The reason is, as soon as this die approaches this ram approaches nearer to this die, what happens? This will be get blocked at this place. Okay, so there will be some material which cannot be extruded beyond this point. Okay, so this material what will become? This material will become wastage. Okay, and what is done, as soon as this ram reaches till this die touches this die, this material is cut away from this point. Okay, so from this point this material is cut away, and your final product is kept away for further processing. Okay, so this way this waste material is called as butt. Okay, the material which could not be extruded using direct extrusion, this waste material is called as butt. Okay, so this I have even wrote in PPT also. You can read it. The metal block is loaded into a container. Okay, so under this, what is the first step under direct extrusion? We have to load your work blade inside the die container. Okay, and after that, the ram compresses the material, forcing it to flow through one or more opening in die. Okay, at the opposite end of the container. Okay, so at one end we are having ram, and at another end we are having die opening. Okay, and through which your material is coming out. Okay, then there is second point. As the ram approaches the die, a small portion of the billet remains that cannot be forced through that die opening. Okay, so as this ram reaches to this near to this die, there is some portion of work billet that cannot be forced to flow through this die opening. Okay, so this extra portion is called as butt. This is already explained to you. Okay, and is separated from the product by cutting it just beyond the exit of die. Okay, so here there is one more issue. Since your work metal, this billet is sliding against your container. Okay, so since there are two moving surfaces, that is surface of work billet and surface of your die container. Okay, so there obviously there is friction between these two surfaces. Okay, so if this is a problem in the case of friction is not desirable in the case of direct extrusion, but it cannot be removed. Okay, so friction between container walls and workpiece is one big problem in extrusion, and it is so high, you can say higher forces are needed to extrude the work billet in the case of direct extrusion. Okay, so how this problem is is reduced of friction problem is removed in we will discuss in next type of process, that is the indirect extrusion. Okay, so this under direct extrusion, friction is a problem because of the relative motion between the work billet and your die container surface. Okay, then there is another problem with the while we deal with the hot extrusion. Uh, there are chances of formation of oxide layer on the surface of your work billet. Okay, as soon as this work billet goes through the die opening, it comes out through the die opening, and it comes in the contact of your environment. So oxidation of surface takes place, and this is also a not desirable thing. Okay, here under direct extrusion we can see what kind of save what kind of saves that can be generated. Here you can see there is a one direct extrusion arrangement. We have die container, then we have die, and this is your work blade in blue color, sky blue color, you can see, which is being extruded through some kind of arrangement. Okay, so here you can see some we are going to provide some final shape or some circular section to this your extruded portion. So we have some arrangement in your ram. Here you can see some extra some more some part of your ram you can visualize here. Okay, so this part is helping to produce circular hollow cross section. Okay, which is the final shape of your extrusion direct extrusion process. So under direct extrusion process, there are number of cross sections that can be produced using direct extrusion processes. Here you can see circular cross section, hollow circular cross section can be produced. Then rectangular hollow cross section can be produced. Then we have semi hollow cross section. Okay, C shape that can be these types of shapes can be produced using your extrusion processes. Then this is another kind of, there are different kind of I section, L section that can be produced using uh, using your direct extrusion processes. Okay, so under direct extrusion processes, there are number of cross sections that can be produced using your by the application of your direct extrusion. Okay, now we come to the indirect extrusion type processes. Okay, so here you have to visualize what is the difference between direct extrusion and indirect extrusion. Okay, so first let us focus on figure A, then we will come to the figure B. Okay, so this is your figure A. Under this is your container, this is your die. Okay, and this die, you can see it is, it is kept with your RAM. Okay, this is your hollow RAM. Okay, so here you can see this die is moving with the RAM. Okay, and this is your work blade, which is initially kept under this your die container. Okay, so if somebody has unmuted your mic, please mute your mic if you are not, if you are not having any query. Okay, so this your work blade is kept under your container, and here you can see the direction of force. Force is being applied from left to right on your RAM. Okay, so as soon as this force is applied from left to right, what is happening? Your die block is moving. Okay, as soon as this die block starts moving towards left, what happens? There is a compressive stresses are generated on in the work blade, and your material starts coming out of your die opening. So here you can see the direction of material flow is from right to left, and the direction of RAM is from left to right. So that is why it is called as backward extrusion or indirect extrusion, because the direction of force applied is opposite to the direction of material flow here. Okay, so here we are having a RAM which is hollow, and with a die is attached to this hollow RAM, and your material is coming out of your die opening because of compressive stresses generated in the work blade. Okay, this is how your indirect extrusion takes place. Okay, this is a case of hollow RAM. Then we can come to the figure B, where some hollow cross section is being produced. Here some solid cross section was being produced. Here some hollow cross section is being produced. How this hollow cross section is being produced? Here you can see we have this die. Okay, on which certain force is being applied by the RAM, which is moving from left to right. Okay, so as this RAM moves from left to right, this is solid RAM, and it has a slightly less diameter. This die has slightly less diameter as compared to the container diameter. Okay, so this is how this hollow cross section is being produced using your backward extrusion or indirect extrusion. Okay, the process is same, but the direction of flow of metal here you can see it is opposite to the direction of force applied. Okay, so we are applying or you can say it is opposite to the direction of RAM movement. The movement of material flow is opposite to the direction of RAM movement. Okay, so here hollow cross section is being produced, here solid cross section is being produced. Okay, there are a number of configuration, even there are other type of cross section that are also possible. Like in the case of direct extrusion, we were discussing hollow circular shape, hollow rectangular shape, and semi hollow cross section shape, and this kind of arrangement are also possible in the case of indirect extrusion processes or backward extrusion processes. Okay, so here one important advantage that is noticeable in the case of indirect extrusion, that there is no relative motion between container wall and work billet. Okay, so in the case of extrusion, what was the major issue? Friction between container wall and workpiece is one big problem in the case of direct extrusion. Okay, but since in the case of indirect extrusion, there is no relative motion between the surfaces of your work billet and your die container, so this friction phenomena is reduced. Okay, so or there is very slight friction that exists. Okay, so obviously in the case of indirect extrusion, the requirement of force, that is force requirement to extrude the work billet, is less as compared to your direct extrusion processes. Okay, so the same literature I have wrote in the point form. In the case of die, in the case of indirect extrusion, the die is mounted on the ram rather than at the opposite end of the container. Okay, so in direct extrusion, what we were having, we were having a ram at one end and die was mounted on the opposite end. But in the case of indirect extrusion, it is mounted on the ram. Okay, and as the ram penetrates the work, the metal is forced to flow through the clearance in a direction opposite to the motion of ram. Okay, so in the case of direct extrusion, the metal was flowing in the direction of motion of ram, but in the case of indirect extrusion, it is moving opposite to the direction of motion of your ram. Third one, it is the advantage, you can say, of indirect extrusion, that billet is not forced to move relative to the container. Okay, so there is no friction at the container wall and the end. The ram force is therefore lower than the direct extrusion. Okay, so this is all about you can say indirect extrusion, but there are obviously some disadvantages, or you can say limitation of your indirect extrusion. The major limitation of indirect extrusion is that the lower rigidity of your hollow ram, and it is difficult to support the extruded product as it comes out of your die. Okay, so the handling of material or the support that is needed, which is support needed for the final product that is coming out of your hollow cross section, is a big problem in the case of indirect extrusion. Okay, so some arrangements are needed to support the material which is coming uh, out of your die opening in the case of your indirect extrusion. Okay, now we will come to the next type of classification, that is hot and cold extrusion. Okay, so this is normally same in all processes. Under hot extrusion processes, what we have to do, we have to heat the material beyond the recrystallization temperature. Okay, so obviously this heating has a uh, common advantage between all bulk metal forming processes. It reduces the strength and increases the ductility of your work billet. Okay, so obviously under hot extrusion processes, the force requirement is low as compared to cold cold extrusion processes. Okay, as well as there are some other advantages that are associated with hot extrusion processes. Okay, so these thing you can read. I will move a bit quick. Okay, so here this is the example which I gave in starting for the product that are produced. These are door and window frames. These are produced using your extrusion processes. Okay, so under hot, it is well known that the material or the work billet is heated above recrystallization temperature, and what it causes, it reduces the strength and increased ductility that I have already told, And okay, and because of this reduced strength, what happens? There are advantages because of reduced strength and increased ductility. What is happening? There is reduction in the ramp force and increase in the ram speed. Okay, so this was all about hot extrusion. Okay, then we will come to the cold extrusion, and the cold extrusion near net finish, or you can say close tolerance can be achieved because there is no distortion in the final product due to cooling. Okay, because the process is carried out at room temperature. Okay, so generally cold extrusion is carried out using impact energy, or it is called as impact extrusion. Okay, because very high energy is needed to extrude the material at room temperature. Okay, so there obviously there are certain advantages why this cold extrusion is carried out. These advantages are increased strength due to strain hardening. Close tolerance are possible, as I already told why these close tolerance are possible, because there is no shape change or distortion in the finished product because of cooling. Okay, because there is no change in temperature, so close tolerance are possible. Improved surface finish, since there is no heating, so there is no oxidation layer, and the production rates of your cold extrusion processes is high. Okay, then we will come to the next type of classification.
Sir,
Okay.
I have a doubt.
Yes.
Sir, what is close tolerance?
Close tolerance means we have more accurate product. Okay, the dimensions are more accurate as compared to your other process, that is the hot process. Okay, close tolerance means a zero dimensional inaccuracy. Okay, closer to zero dimensional accuracy. Okay, got it.
How it is
Okay.
different from surface finish?
Uh, So surface finish is another thing. Okay. So surface finish, we are talking irregularities on the surfaces. Okay. These are in micrometers. Okay. But when we are talking about tolerance, we are talking about the overall dimensions of your workpiece. Okay. In tolerance, we are talking about overall dimensions, length, width, height of your workpiece. But in the case of surface finish, we are talking about the surface quality only. Okay. So how these terms are different from each other. Okay. Okay. So fine, we will move to the next type of classification, that is the continuous or continuous extrusion and discrete extrusion. Okay, so under continuous extrusion, what we have, this process is used for producing very long section in one cycle. Okay, but but you can say the continuous extrusion is also limited by the size of your static billet, because we cannot have the starting billet of unlimited size, because there is certain limitation on the size of billet that can be loaded your in your extrusion container. Okay, so in nearly all cases, the long section is cut into smaller length in a subsequent saving or shearing operation. Okay, so under extrusion, continuous extrusion processes, what we are doing, we are producing a very long cross sections. Okay, and in the case of discrete extrusion, what we are doing, we are producing single parts of smaller dimensions as compared to continuous extrusion processes. Okay, and under discrete, you can take example of impact extrusion, in which a final product is produced by applying the impact energy. Okay, so this was all about about the classification of your extrusion processes. Now we will come to the slight analysis, which is important when we discuss about extrusion processes. Okay, so this is the simplest arrangement about to understand the analysis of extrusion processes. We have this die container, then we have die, then work plate is being kept in your die container, and it is coming out of your die opening. Okay, coming out of your die opening. Okay, so here there are certain nomenclature. AO is your initial diameter. Okay, and is your sorry, not diameter, cross sectional area of your initial work billet, and AF is cross sectional area of your final work shape. Okay, so this is the extrusion ratio. How this extrusion ratio is given: Rx equal to AO upon AF. Okay, initial cross sectional area divided by final cross sectional area. Okay, this is the extrusion ratio. Then how these true strain are calculated: as epsilon equal to natural log of AO upon AF, or a natural log of your Rx, extrusion ratio. Okay. Okay, so then the pressure which is generated inside your work plate, it is calculated as P equal to YF natural log of Rx. Okay, so or you can say YF into epsilon, because this natural log of Rx is equal to true strain. Okay, so the pressure that may be given as P equal to Y bar F is multiplied by true strain, that is the epsilon. Okay, so this Y bar F is nothing but it is your average flow stress, and it is given as K epsilon n upon 1 plus m. Okay, this we have discussed multiple times in previous lectures also. Okay, so this is how this calculation of pressure is done in the case of direct extrusion process. Okay, so here this is noticeable that we are discussing about ideal case. Okay, under ideal case, this pressure is given as P equal to YF natural log of Rx. Okay, so uh, okay, so under the conditions when friction is considered, this extrusion strain is given as epsilon x. These are the all formulas that you have to remember. There certainly there will be few questions, numerical questions, that will be based on these formulas in your examination. Okay, so maybe I will try to take few numerical questions so that it makes you easy to understand how you have to solve these or you have to use these formulas while solving the numerical problem. Okay, so under direct extrusion, when this friction is considered, the extrusion strain is given as epsilon equal to A plus B natural log of Rx. Okay, so the values of A and B, these are the constant, and the values of A and B are: A is normally 0.8 and B varies between 0.1, 0.2 to 1.5. Okay, so these values will be given during your examination when you have to solve the numerical problem. Okay, so for indirect extrusion, the pressure is given as P Y bar F epsilon x. Okay, so what is changing here? When we are considering friction, this epsilon x is changing. Okay, this earlier this epsilon x was natural log of AO upon AF, but now here the epsilon x is your A plus B natural log of Rx. Okay, so for direct extrusion, pressure is given as Y bar F epsilon x, and for this was for indirect extrusion, and for direct extrusion friction is higher, so this length of your work blade and initial diameter comes into picture, and this force P is calculated Y bar multiplied by summation of epsilon x plus 2L upon dO. Okay, and the ramp force in the case of indirect or direct extrusion is calculated as F equal to P into AO means a initial cross sectional area of your work plane. Okay, suppose if V is the ram velocity, so this is how the power requirement is calculated. Capital P is equal to F V. Okay, so where V is your ram velocity and F is your ram force. Okay, this is how the different items, that is the pressure, force or power requirement, are calculated in the case of extrusion processes. Okay, now we will come to the
Sir,
extrusion. Yes.
sir, in the previous slide, A and B,
Yeah.
how these are calculated?
This is normally
Small a.
uh, A is already practically calculated by different researchers. This A is constant 0.8 for all type of material. Okay, and B varies
Sir, B,
between 1 point. Yes,
sir, B will
and
depend on
B,
material
B will depend on material.
and the
B will
coefficient of
vary
friction
from
also.
no, it vary from material to material. It is not on friction. Okay, so here you can see that for uh, actually this B is coming because of friction, but this variation is not much when we are taking different materials. Okay, so this B ranges from 1.2 to 1.5. This is well established value. Okay, so maybe I have not gone through the depth how this B was calculated by researchers, but the value varying from. So,
Sir, your
so
voice is not audible.
okay, there was some call. That's why my voice gone. Okay, so this is how now my voice is very audible.
Yes, yes, sir.
Okay, so I think multiple people has unmuted their mic. Other please mute. Only one person speak. So there might be some theories that researcher might have developed. I have not gone through that theories. Okay, that I will check. Okay, so how this B is calculated, but here for now we can note down that the B varies from 1.2 to 1.5, and it is different materials. Okay,
So it is not a strong function of coefficient of friction.
that I have to see. Okay, I'm not sure. Okay, so I will go through the more literature and I will see how this B is related. Okay,
Okay, sir.
okay, I will see that how this B is calculated. But for now, we can note down that B varies from 1.2 to 1.5, and it is different for different materials. Okay, and maybe it might be having a correlation with the friction also. That, but I have to see. Okay, I'm not sure. Okay. So this I will check again, and I will let you know maybe in the next class tomorrow that how this B is being calculated and what are the different research that has been done to calculate this B. Okay, because in books, in normal books, you will find only numerical ranges. Okay, so this is how we will proceed ahead. Okay, fine.
Yes, sir.
भरत, हाँ
Yes,
ठीक है
sir.
ना, इसको मैं देख के बताऊंगा है ना कि
Sir,
कैसे
I was
calculate
asking is
करते
because the whatever the force requirement that will strongly depend on B, and B is
हैं.
a
हाँ,
function of the material properties, and we can accordingly control. Maybe if it is a property of container, then we can control the container in such a fashion that the force is minimized.
okay, okay.
That was asking.
So I will check and tell you with better clarity instead of guess. Okay.
Okay, sir.
Otherwise, it may create confusion, na?
Yes.
Okay. Okay. So fine. Now we will move to the next topic, that is the extrusion dies and presses. Okay. So here you can see this was your container, and this is your die. Okay. So here you can see this angle is called as die angle. Okay, and this die angle has some important role in the case of direct extrusion or indirect extrusion. Okay, so under direct extrusion, the effect of die angle you can see here. If the die angle is very low, the friction is very high. Okay, if the die angle is very low, the friction is friction is high, and if the die angle is very high, in that case also there is turbulence, and which increases your ram force. Okay, so here you can see if we are having low die angle, and there is a plot between the ram force and die angle. Okay, so initially this ram force is decreasing, and after that there is a optimum value. After that, this die ram force starts increasing. Okay, so this value is your optimum value of your uh, die angle. Okay, so we have to decide accurate or optimum die angle in order to reduce your ram force requirement in the case of extrusion processes. Okay, so these are number of formulas which are given in books. Uh, so the effect of die orifice, that is die opening, can be assessed by the die shape factor, and it is expressed as follows. Okay, so this is a die. This is the formula for calculating the shape factor of your die orifice, and it is given by researchers. I have not gone through the derivation how this is calculated. Okay, I have just note down from the books. The shape factor is given as kx equal to 0.98 plus 0.02 cx upon cc. Okay, so kx is your die shape factor, cx is the perimeter of your extruded cross section. Okay, cc is perimeter of your circle of same area as the extruded shape. Okay, so for circular shape, kx is 1. Okay, it can be understood that if shape is circular, then cx will be cc. Okay, so if cx and cc are equal, then this will be this term will be 1, and 1 to the power 2.25 will be equal to 1. So this kx will be 1. Okay, 0.98 plus 0.02. Okay, so for circular shapes, this kx is 1, and for kx for hollow and thin wall section is higher than 1. Okay, so this term will have some value, and therefore this kx shape factor becomes more than 1 in the case of hollow and thin wall cross sections. Okay, so for shapes other than round, that is circular, other than circular cross sections, the pressure is calculated as P equal to kx yf epsilon x. Earlier it was yf into epsilon x. Now your shape factor comes into the picture if we are having shapes other than round. Okay, similarly for direct extrusion, P equal to kx yf multiplied by summation of sigma x plus 2l upon do. Okay, so here you can see how complex cross sections can be extruded using your extrusion processes. Okay, so here is a heat sink. uh, the heat sink cross section, you can see, if you see the surface area, it will be quite higher as compared to the size of uh, your uh, uh, extruded section. Okay, so this is how this type of cross sections or multiple type of cross section can be extruded using your extrusion processes. Okay, this is showing your complex heat sink that has been extruded using direct extrusion. Okay, so now we will come to the extrusion presses. Okay, so these extrusion presses are the machines that are used to drive your RAM, okay, or to transmit power to your RAM. Okay, so these may be horizontal, vertical, depending upon the orientation of your work axis, and these are generally operated by hydraulic power, and uh, these are used for semi-continuous production of long section, or you can say indirect extrusion. Okay, sometimes these may be driven by mechanical drives in the case of extrusion of individual parts, such as impact extrusion. Okay, so under impact extrusion, the energy is applied by the mechanical drive rather than hydraulic drives. Okay, so this was you can say all about your extrusion processes. Okay, so there are a few kind of defects in extrusion processes, and these defects are major three types of defects that exist in the case of extrusion processes. Okay, that is the center burst, then piping, then cracking. Okay, so under center burst, what is happening? Some crack is generated in the center of your extruded workpiece inside your final product. Okay, and under piping, there is surface cracking inside your extruded part. Okay, and in the case of surface cracking, what happens? Some cracks are generated on the outer surface of uh, your extruded material. Okay, extruded product. Okay, so these are the common defects that exist in the case of your extrusion processes: center burst, piping, and surface cracking. Okay, so